last lesson we learnt about this concept of exponential growth and decay, right? And so we said, okay, if I have some expression which is of this form, what did all these kind of variables mean again? Remind us. What do all these variables mean?
Q is the totals, the amount.
Yeah, so Q.
Initial amount is A.
So Q you can think about it as a quantity.
Yeah.
Yep. Why is A the amount?
Initial amount.
Why is it the initial amount?
Because if t equals to 0, which is the initial time, then it just equals 1, A equals 1.
Right, so if I, it's a lot clearer with numbers, right? If I have y is equal to, 5e to the 2x, or 2t, we generally use, right? So when t is equal to 0, what's going to happen here? I'll just get 5e to the 0, and then I'll just get left with 5. Okay, e to the power of 0 is just 1. So A you can think about as the initial quantity when t is equal to 0. Right? Obviously then t is equal to time. How much time has passed. And K is something a bit different. We call that the growth constant. And I'll explain a bit about that later. Right. So this is our exponential growth and decay sort of model. If we ever are presented with a situation where they say this assumes exponential growth, then we can look at this kind of model. But the model was very special because it wasn't just its original function we were interested in. We could also find its derivative, right? What's the derivative of exponential functions? We're going back to typical numbers, right? If you take the derivative of this, y dash, you're going to get, remember, we take the derivative of this power component and drop it down. The original part stays the same though. So when I find dq dt here, right, what do I get? I get k, yeah, a kq. So we actually looked at this idea, hang on, so k, and I have this original expression I keep, but we've seen that before, right? That's just from here, that's kq. We can just replace it. We can replace this part, a to the kt, with q. Why is that special? Because it's a relationship between the derivative and the original expression. And again, I called that another fancy term, a differential equation. So that was the terminology that I introduced last lesson, right? We have this original expression, and I can find its derivative. And what this means, right, is I'm saying that, hang on, there's a relationship between how fast the population is growing and the original expression. And again, we shouldn't be surprised about that because that's what our definition of exponential functions are, right? They grow much more quickly or slowly depending on how much population there is there, okay? First question, Eva. We looked at, funny enough, we looked at rabbits. How convenient is that? We looked at rabbits growing over time. That was the first question. Second question, Eva. Read it out for me. Big loud voice.
I can't take you seriously with that.
I thought you were saying just in general. Is that? How have we done this?
Okay. Professor Smith has a colony of bacteria. Initially, there are 1,000 bacteria. The number of bacteria, NT, after 3 minutes is given by NT equals 1,000 ET. After 20 minutes, there are 2,000 bacteria. So K equals 0.0347, correct to 4 decimal points.
So what's our expression again? NT is equal to
1,000
I just want you with it. All right. All right. Sorry, seriously. Okay. 1,000 e to the kt. After 20 minutes, there are how many? 2,000 bacteria. Okay. Did anyone have a go at this one?
Yes.
Did you? Yeah? Anyone else? Yeah? No? You want to have a go or do you want me to go through it? No, I'll jog you maybe. We'll go through it first, yeah? Okay. Just to kind of clarify things, right? Here's our model. Right? Some constant e to the kt. If you see something like this, n of t, right? Think about your f of x notation. It's a similar idea, okay? F of x means, we've got some value and we're putting x into it. What's coming out? Same idea of this. I'm looking for the number of bacteria, and the thing that I'm putting in is time, right? I want to see what's changing over time. This one's different to the last example, though. Have a look at both of them. What's different? It's not a trick question.
There's like a K.
That's actually really important. And this is the first common type of question that they put in exams, right? Is that they want you to find the K value first. In fact, the first question says, show that K equals to 0.0347. Yeah, okay. So in the previous question, they gave us K and we were just having to substitute values in to work out what, how many rabbits there were or how quickly it was growing. But in this situation, we actually have to do more work first. We have to find K. The other difference is they give you more information. They say after 20 minutes, there are 2,000 bacteria. So we know how many there are initially. Like we could sub in T equals to 0. We don't even need K for that. Or we could just look at this constant here. There's 1,000 rabbits initially. So that's not too helpful, okay? But what is helpful is this piece here. Because after 20 minutes, there are 2,000 bacteria. So that means if T is in minutes, which it is, then what can I substitute in? What values can I put in?
2,000 e to the power of 20k.
Yeah, right. So this is saying, this is like a word expression what's going on. Let's think about a mathematical expression. N of T, that's 2,000. But T, that's 20. All right, so we put that all in. We get 2,000 is equal to 1,000 e to the, now KT, well, if I know that T is 20, I can just rewrite that as 20k. Okay, I'm just substituting T as 20, then multiply together. I've got 20k there. This is looking familiar, isn't it? What kind of equation is this? Exponential equation, right? Because we've got an unknown in this power. When I've got that Angus, what do I like to do? I've got an exponential equation, I've got an unknown in the power, how do I solve for it?
You have to get E 20k by itself.
Yeah. Good. So remember that if we just take the log straight up, then we run into problems there, right? We don't want to do that anymore. But first, let's try and get any constants that we have to the other side, all in one kind of value. So we'll divide both sides by 1,000. There's a 2 there. E to 20k. We can take the log, and particularly the natural log here, because it just becomes a lot nicer, right? We take the natural log of both sides, base E. What rule can we apply now?
Coefficient.
Yeah, the power rule. Bring it down as a coefficient. Right. And this is why we chose base E, because, well, ln of E, or log base E of E, right? Remember, that's just saying, hang on, what do I need to raise E to the power of to get E? That's just 1. That would just simplify out as 1, right? Which leaves us with K is equal to, divide both sides by 20, ln on 2 on 20. Chuck it in for me.
Equals to that number.
37.
47.
But is there more?
Yes.
What's the next
Well,
one?
I'm pretty sure it was 6.
6?
It was like a 3, 4, 6.
0, 3, 4, 6, 5, 7.
Oh, okay. 6, 5, 7?
Yeah.
Yeah. Now this is actually a really important step, because if they're giving you the answer, show, right? You have to convince beyond reasonable doubt that you've done that. Because everyone, like I say, anytime we've got a show question, students are going to end up with this answer. Doesn't matter what they do here, somehow they'll get 0.0347 at the end. So just show beyond reasonable doubt that you say, oh, okay, I actually know that this is not exactly equal to that, but if we round it, so to 4 dp. Right. Now, a question from last lesson remains, hang on, in next parts now, am I going to be expected to use this, or do I use this? Because this is kind of more an exact form where we haven't rounded it. And the answer is, well, because they've given you this, it actually doesn't really matter. You can use this one, you can use this one without any consequences. Generally though, if it's not specified, we want to use the unrounded value just because it's more accurate, okay? But if they've kind of said, okay, show that K is equal to this, that's actually giving you like a free pass to essentially use that value, right? So it's kind of dependent on the question. Harry, what's the next one? Okay, so let's go back to original equation now. So then, let's go ahead and say, okay, Well, when t equals to 120, or using my kind of like f of x notation, n of 120 equals to 1000 e to the 120k. Now for k, I mean, I still like using the exact value stuff, so I want to use that. Yep, defying. Alright, let's calculate that out. Answer B, 64,000. Is that what we're getting when we put it in? That's. Sorry? 6,000. Do we put it? So are we putting in the 0.0347, or are we using the? Which one are we using?
I'll try and
I'll do it myself.
I used the rounded one.
Wait.
I used the precise one.
Wow, it changes actually quite a lot.
Does it actually?
It does.
It does. That's like a 328 difference.
Yeah.
That's
Just like
interesting.
one decimal. Wow.
Yeah.
I used the unrounded.
So don't use the unrounded?
Yeah, like I'm saying, in this situation, either way, they would probably give it. Show that k. Maybe we can just use the rounded one. Doesn't really matter.
Big difference though.
It is, but like I said, it's a model, right? Because all of these are kind of approximations, so it doesn't really. Let's just use the unrounded one because that's always safe. Right, so that's B. C, what do we need to do for that? When you're talking about rates, Joel, what am I thinking of? When I see a rate of change, I want to know the rate of change of the number of bacteria per minute when t equals to 20.
So you want to get the differential of the differential equation.
Yeah.
So the rate of change.
Yeah, that's right.
Just kq, so you get k times the unrounded form,
Ah.
and then you get 2,218.0709.
So Joel's realizing I don't even have to really do much differentiation here, right? Like what I could do is I could find, I guess if we're using this notation, right, n dash of t, which would be, k times 1000 e to the kt. And you notice how I'm using k here because, I don't want to keep writing out ln on 2 on 20 because I know what k is equal to already. So I can just write k as a variable that I know what it is. So I'm just going to leave it as k for now. Two methods, right? When we have something like this, I can either substitute into this value what t is equal to, so 120. So you can find n dash of 120 and substitute that in. Right? Or what we can do is we can say, oh, hang on, I know this relationship between exponentials with their original expression and the derivatives. I can just say, well, n dash of 120 is going to equal to whatever my k value is, which is we're using the unrounded form, so ln on 2 over 20 times however many bacteria there are, 64,000. Right, so either way is going to work. Just depends which one you're more comfortable with. Again, it's always safe to just differentiate and check, but this is a relationship, something you can use as well. Okay? Let's find that out.
So you can use differentiation, please?
Yep. Because that's what, I've used n dash here, right? But that's just differentiation. But that's what dq dt is actually saying, right? Because what's that saying? It's saying it's a rate of change, right? I've got this quantity. How is it changing with respect to time? That's what dq dt is actually saying. So anytime you see rate of change, okay, that's what I want you to be thinking about. What is our rate of change? Put it in for me.
2,218.0709.
0709. Blah, blah, blah. And again, we're dealing with what? Bacteria, right? So it can't really have 0.07th of bacteria. We can just round off to the nearest whole number. But just specify what you're rounding to. Bacteria per minute. So that's the rate of change. That's how many bacteria that are growing per minute. Now, obviously, with exponential growth, right, it's continuous. So it's only in that minute each minute, the rate of growth is actually going to be changing. Okay. All right, part D. Part D. Kyle, read out for me.
How long does it take for the bacteria to increase from 2,000 to 100?
Okay, so this one here now. How long does it take for the number of bacteria to increase from 2,000 to 100,000? So obviously we have to know two things. We have to know when does it hit 2,000, we already know that. When does it hit 100,000 though? We can work that out, right? What do we need to do for that? The key part for this one is we know we have an expression already, right? That we can actually use. 1,000 e to the ln on 2 on 20 times t. That's our kind of expression which represents how many bacteria there are. How do we use that?
Substitute in the 100,000 and then start breaking the equation.
Yeah, right. So let's think about what we're trying to find. You're trying to find how long does it take you to get to 100,000 bacteria. I know that the number of bacteria is growing over time, right? But how many are there? Or sorry, how long does it take until there's 100,000? Just think about which information you're substituting into. James has told me, well, I want to put this as my end value because that's what I'm looking for. That's where I can substitute it in, right? So we got 100,000 is equal to 1,000 e to the, and again, like I can just leave k here until I've like put in like the final step, which is just quicker to write. But just keep in mind that you've got k already. That's not an unknown variable. You've got that from over here, or you can use 0.0347. That's fine too. Right? So I've got that here. And I've got some nice numbers here because they're going to simplify out quite nicely. You just cross off 3 zeros. So I get left with 100 is equal to e to the kt. And that's our usual exponential kind of equations, right? We're pretty good at this now, hopefully. Taking the logs of both sides. And then using our power of a power rule to drop it down. But don't forget, like, I've written just k just to save myself time. If that's not too clear that we've got that k value, you can write 0.0347 or ln on 2 on 20 each time. It's just to save me a bit of time there, right? Whichever kind of works for you. But what's the actual unknown in this expression? What are we trying to find? Time, right? How long? Don't forget that. How long? So we can just rearrange t. I know ln of v, that's just 1. So you just write 1 there. We've got t is equal to ln of 100. And now when you're substituting in, you can put in your 0.0347 or ln on 2 on 20. Which you should get. What do you get? 132.877. So that's our answer, right? 132.87. What do you mean?
Isn't that the amount of time it went from the original to 100?
Okay, so it's actually a bit mean here, right? Can you see? They've actually asked not how long does it take to get to 100,000, but this is where students need to read questions very carefully. They say, how long does it take to get from 2,000 to 100,000? How long does it take to get to 2,000? 20 minutes, right? So it took 20 minutes to get to this point already, then we need to subtract it off this one. Is that what you're saying? Right. So again, let's just subtract that off. So we've got 132.877 minus 20. What are we getting? 112. Right. So, or again, we can just round to whichever one we please because this is a model, right? It's not saying, we have to write it in its exact form because we're working with discrete things on a continuous model. There's going to be points where things are, in the process of growing or something like that. That's why we have these kind of values here, right? 113 min.
With all these questions, do you have to round it? You can't have that many minutes, like 100.
Yeah, that's a good question, right? Like time is continuous, okay? And Laura's right, you can have 112.8777 as opposed to like the bacteria that we're looking at. Here's the interesting thing there, right? This is just this is more of a pedantic thing, but for example, like think about the question, saying how long does it take to get from 2,000 to 100,000? So if you put in like 112.877 into this, that's the moment that you will get 100,000 bacteria, right? What happens if I put in 113? I'll have more. So strictly speaking, right, 113 is not the answer to get from 2,000 to 100,000, okay? But I think the emphasis is that we're creating a model here, okay? And that they'll accept some sort of rounding situations. Exactly right, and as long as, the important part is as long as you specify what you're rounding to, okay? So you could perfectly, for example, like with bacteria, right? Someone might argue, well, even if this was like 2218.9, you know, if you're rounding that, that would be 2219, okay? But if you can argue, oh, you know, there's only like 0.9 for bacteria, doesn't really count. I only have 2218 whole bacteria. You could say I'm going to round in that way because of that reason, okay? So I think the important thing is when we're rounding, it's fine to round, but just need to specify how you're rounding. Okay, that's the kind of important takeaway there. Questions about this one? Hopefully we can see that I think the hard part is just deciphering the language and working out what you need to do. The tools that you already have. You know, algebra, taking logs of both sides, solving exponential equations. That's the kind of heart of this problem.